All right. Do you guys like my new way of testing? So that is a spiral didgeridoo, which I did not know existed until this weekend, and I had to get one. So there you go. That's what a spiral didgeridoo is. Apparently, you can just take a didgeridoo, which is a very long kind of tube, and literally just put it in a spiral, and it still works. All right, so today we're going to be looking at a paper called Dynamic 3D Gaussians Tracking by Persistent Dynamic View Synthesis. This is kind of an extension of one of the works that we looked at last week that was all about these 3D Gaussians, which are kind of a new 3D format that's taken the world by storm here, kind of coming up against NeRFs, which I would say is the kind of biggest competitor to dynamic or 3D Gaussians. And what's interesting about this paper is that whereas most NeRFs and the 3D Gaussian paper that we read before are static, which means that it's basically a frozen static scene, these are they include the dimension of time. So here we have some videos. You can see here this guy throwing a ball here, and this video is made entirely of 3D Gaussians. So this is what the center of each of those little Gaussians look like. So it's almost like a point cloud of little Gaussians, and if you only look at the centers, it just looks like a bunch of dots, but each of those Gaussians has some spread, right, some variance, and that's why you can get this kind of full effect. Pretty impressive stuff. So this is work coming out of Carnegie Mellon University, which is where I went to school, Aachen, Germany, and then this same INRIA University Côte d'Azur en France, which is actually the same research group as the one for the original 3D Gaussian paper that we read last week. So another thing I noticed here is this background. I was like, what the hell is this giant geodesic dome that they're standing in? And I actually went ahead and looked that up for you guys beforehand. So this is what they're standing in. It's a giant studio. It's a radius of 5.49 meters, total height of 4.15 meters. The center of the dome is a height of 1.4 meters. It was raised above a hemisphere to allow increased access to the edges of the dome. It's 6 pentagonal panels, 40 hexagonal panels, and 10 trimmed base panels. So it's this giant camera dome, and there's a camera right in the middle of it, but then there's also little cameras all around the side. So each one of these little dots is a camera, so it's a huge amount of cameras inside this giant dome. Let me actually see if this tells you a little bit more about it too. The studio houses 480 cameras synchronized to a central clock system. So what's nice about that dome is that basically you can take 400 pictures instantaneously at the same exact point, and because this is a stable static structure, you know the exact position of every single one of these cameras, right? You went in there beforehand with a little checkerboard and you basically calibrated every single one of these cameras, so you know that every single picture is taken at the same exact time, and you know the exact position of the camera when that picture was taken. And it's a little bit of a cheat code for sure. This is not the first time that it's been used in kind of the original volumetric representations paper, NeRF. I think it might have been this one. Yeah, and I'm going to have a hard time finding this, but in the original Nerf paper, I'm pretty sure they used one of these camera spheres as well. And obviously you don't have one of these things at home, but you know, they're pretty good. 5 Kinects. Kinects are structured light cameras that used to come with a Xbox, and they became very popular in robotics because they actually work quite well. So Kinects give you explicit depth in the form of point clouds, but they're not going to be using that for this work. All right. Enough dancing around. Let's actually get into the meat of this. So, abstract. We present a method that simultaneously addresses the task of dynamic scene modeling. Or, one second. Okay. I just had to click on a thing over there. We present a method that simultaneously addresses the task of dynamic scene novel view synthesis. So novel view synthesis is creating images from a view that you haven't seen before. So the camera trajectory of this is not, there was no camera there, right? This is a virtual camera trajectory. It's a novel view. There's a bunch of novel views. This is probably 30 frames a second, and it's kind of panning around. And then the dynamic refers to the fact that the scene itself is dynamic, right? So the scene is changing over time. It's not a static scene. 6 degree of freedom tracking. 6 degree of freedom. Degrees of freedom are, I guess, a degree of freedom. So 1 degree of freedom might be X, Y, and Z, and 6 refers to X, Y, Z, and then the 3 rotation degrees of freedom of all dense scene elements. So I think what they're referring to there is that, especially in these visualizations here, you see this kind of like rainbow stripe kind of thing that's like leaving the body. What that means is that there's a little Gaussian that represents a specific point in space, maybe the elbow of this guy, and as this guy's elbow moves through the scene, the little trail there shows you how that point in space is moving. So it's kind of an interesting way to treat dynamic scenes, right? A lot of the way that we do dynamic scenes now with textures and meshes, as you would have in a video game or in a CGI, right? You're representing objects explicitly as meshes and textures, and those meshes and textures have some velocity and that have some position and they have some orientation, right? And what a game is, or a video game largely is a bunch of logic and code that changes the position and orientation and relative placement of these different things. That's very different from a Nerf. A Nerf has no explicit notion of the objects in the scene, right? A neural radiance field is just a little neural net. It's a tiny little neural net, this little f of theta here, that is storing all of that explicitly. Or implicitly, sorry. So it can tell you what this scene is going to look like from a specific point of view, but it doesn't know, it doesn't really have any concept of what's in that scene, certainly not in the sense of like, okay, if this truck here was going to get flipped upside down or something like that, or rotated, like what would that look like? Versus these 3D Gaussians, you can move them around, right? They're like little points, so you can move them around. So because they're explicit, now you can basically move them, and I think that's what this entire paper is going to be about. It's going to basically be how do you move these little 3D Gaussians over time to create the illusion of a kind of a dynamic scene that you can look from any point of view. Moin moin. I don't know what that means. They call me Ken. I'm sorry. Novel view, unseen renders of color images and depth maps. So these are the depth maps, the lower half of this triangle. A depth image is here in this kind of grayscale coloring. The black means something that's very close, and then white means something that's far away. So obviously this person here is fully black because they're close to the camera, and then this little child here is a little bit further away. That's why they're slightly less gray. 5 scenes and 2 views. So I guess these are 5 scenes and then 2 views. So this is the same point in time, but just from the front view and then the back view. Each scene is parameterized by 200 to 300,000 dynamic 3D Gaussians. And this is what we saw in the first paper, is that the actual number of these Gaussians is a little bit intense, right? You have, I forget what in the paper, I forget they had like 1 million, but like it's a lot. It's a lot of little Gaussians which are tracking over time, and it still blows my mind that modern computers are fast enough to deal with this amount of objects moving around. We render with occlusions the 3D trajectories of 2.5% of these over the last 15 time steps. Okay. So here we're getting a little idea. 15 time steps is 0.5 seconds, which means that this is 30 frames per second, right? 1 second would be 30 time steps. So that kind of tells you a little bit of the frame rate there. Model scene is a collection of 3D Gaussians which are optimized to reconstruct input images. So the reconstruction loss is generally what you're using for this optimization process of how do you get the initial little 3D Gaussians that you're then going to be tracking over time. And a reconstruction loss is basically just trying to recreate images that are the ground truth images, right? The images that are coming from the cameras in this giant array of cameras in this giant geodesic dome here. I'm going to put this here just so I can easily go back to it. My mouse is dying. Ugh. All right, there we go. To model dynamic scenes, we allow Gaussians to move and rotate over time while enforcing that they have persistent color, opacity, and size. Okay, so move and rotate over time. So there's a velocity, but then there's also a angular velocity, perhaps acceleration, angular acceleration. We'll see whether they choose to just stop at velocity or whether they also have the acceleration component, because it's just more stuff to keep track of. But each of these Gaussians has the same color, opacity, which is kind of how see-through it is, and then size, which is, of course, the relative size. By regularizing Gaussian's motion and rotation with the local rigidity constraints, okay, so they're going to be using local rigidity constraints, locally rigid, so whatever little Gaussians are all together in one place, they have some constraint in this optimization process, right? Some regularization to this optimization that is going to force them to be locally rigid. This probably makes it work, but right off the bat, you know that there's going to be situations where you don't have local rigidity constraints, right? If you were looking at a video of water that is turbulent, right? That is not locally rigid at all, right? Every single part of that water is moving quickly and changing with respect to the little local neighborhood. So the local rigidity constraint probably works well for these type of scenes where the things aren't really deformable. They're not really changing or relative to each other very much, right? You have these kind of like harder objects, but for anything soft like smoke or water or anything like that, maybe this local rigidity constraint actually is a negative. We show that our dynamic 3D Gaussians correctly model the same area of physical space over time, including the rotation of that space. Okay, so obviously if you have move and rotate, you're going to have rotations. Dense 6DoF tracking and dynamic reconstruction emerges naturally from persistent dynamic view synthesis. Okay, so if you have a bunch of little Gaussians that you're enforcing to be locally rigid and you're moving them over time, that means that you're going to be able to basically just get tracking for free, because you can just say, okay, well, what is the position of each of these little Gaussians? And look at that. I just have tracking now if I wanted to have that. Without requiring any correspondence or flow as input. I think here they're referring to correspondence is in multiple, let's say you had, let me do this, optical flow. So in this picture of a car, right? You have these cars. They're moving on this highway. You say, okay, this car here corresponds to this car here, right? So in two images, you're creating a correspondence between this part of this image and this part of that image. So you're saying these are actually the same car, and then something like optical flow, what that is telling you is telling you, okay, well, this car moved this much between these frames, right? So here is optical flow for some people coming out of a football stadium or soccer stadium for you American people. I guess I'm American too. I call it soccer as well. But you can see how, okay, this orange boot for this player corresponds to this orange boot from the previous frame and corresponds to this orange boot from this next frame, and therefore there's some motion of that over time, and that's what these optical flow pictures are showing. But normally that would be like this whole separate thing that you would do, right? Tracking or optical flow or correspondence between frames. And having to do that explicitly and separately is annoying. So if you can just get it for free by doing this 3D Gaussian over time, that's actually quite good, right? Because it means that any other problem or other technique where you had to have optical flow, or you were trying to get optical flow for some other reason, now you should just make your whole thing a 3D Gaussian, and then you get all these other things for free. So this being able to get other things for free is actually a very appealing property of these 3D Gaussian representations. We demonstrate a large number of downstream applications enabled by our representations, including first-person view synthesis, dynamic compositional scene synthesis, and 4D video editing. I'm tongue-twisting myself here, but this is the first-person view, so obviously you can put the camera just where the person's head is, right? It's a novel view, and you can render it from that, so look at that. And you get the tracking because you're centering the camera on a specific little Gaussian. You can compositional dynamic scenes. So compositional here refers to you're composing multiple elements together. So here they're just kind of adding 3D Gaussians that are related to them throwing a ball around, and they're putting it onto this unrelated 3D scene. But one thing to notice here is that there is no lighting, right? So one of the hardest things about composition like this, especially if you're doing CGI, is the lighting. So there's, especially in a natural scene like this, the lighting is very complicated, right? You have potentially street lights, you have the sun, you have a couple different objects which might be reflecting light. So the way that light is coming into this scene and bouncing around these different things is actually pretty complicated. And relighting objects such that they appear as if they are naturally in that scene is actually incredibly complicated. And it doesn't look like they're doing any of that here, right? Because the little Gaussian of him passing the ball was captured in this giant circle, which is designed to have a kind of a uniform, generic, kind of soft white light, right? These kind of geodesic camera domes. They're designed to have a very generic white light, but soft light. But that's it looks out of place because it's not the same light as this garden, right? The same thing here. You look at here, it just doesn't quite look right. Same thing, the reflections on the table aren't quite there. And if you guys have ever seen the Mandalorian Unreal Engine, so yeah, I forget, maybe it's this one. Might be this. There's a really nice documentary that I would recommend. It's a little YouTube video, but it might be this one. No, I think it's this one here, this first one. Yeah, but basically they filmed this entire Mandalorian inside this giant studio lighting, or inside this giant studio, right? This giant like screen that goes around. And one of the hardest things that they had to deal with is that the Mandalorian's helmet is reflective, right? Like the people who designed this costume were like, hey, we're going to have his helmet be super shiny. And it ended up being a huge pain because it means that if you're putting him in a CG set, you have to match that exact lighting, right? And it's very, very complicated and difficult to do that. So they have, if you guys have ever seen these TV set lighting circles, lighting spheres. Yeah, no, this thing, lighting sphere. Maybe one of you knows what this is actually called on stick. Yeah, these things. Here you go. So if you've ever seen these in a kind of a movie set scenario, what these are is basically that. They're these little devices that you can use to measure what the light looks in that particular environment so that you can hopefully recreate it in your VFX software. So I don't know, a little tangent on lighting there, but that was one of the first things I noticed here is that there's no notion of lighting in these composition, right? Maybe a future work direction for one of you guys who's into this. Persistent dynamic 3D world modeling would be transformative for both discriminative and generative artificial intelligence. So Generative artificial intelligence is generating things, right? Like generating an image from text. Discriminative artificial intelligence, that's not like a terminology I see very often, but I guess what they're talking about is maybe like tracking or object detection. If you had some camera at an airport that was just counting people, right, it's trying to discriminate. Maybe a cat dog image classifier would count as discriminative artificial intelligence. On the discriminative side, this would enable a metric space reconstruction of every part of the scene over time. So you could measure the distance between things. Modeling where everything currently is, where it has been, where it's moving is crucial for many applications, including robotics, augmented reality, and self-driving. Very true. And I think one thing that they don't even mention here is physics, right? Right now, with a nerf, like one of the things that would be extremely difficult for nerfs to be applied to something like video games is the fact that there's no physics, right? Like what if you had two of these nerfs that represented these Tonka trucks? How do you get the nerfs to represent a collision between these two little trucks? That doesn't make any sense, right? These nerfs are just little neural nets. How do you represent some kind of physics interaction, some collision geometry between two neural nets that are implicitly holding this representation of an object? That would be much easier with something like these 3D Gaussians, right? Because, okay, well, you can just say, okay, well, there's a bunch of little 3D Gaussians. These little 3D Gaussians represent this baseball bat. Therefore, if this baseball bat hits something, we just have to look at the relative velocity of these little Gaussians here and then maybe use that to get the trajectory of the ball, right? So 3D Gaussians are potentially the way that we get physics-based interactions into these 3D representations in a way that we can use them for robotics and games and augmented reality, VR, and stuff like that. In generative AI, such models could enable new forms of content creation, such as easily controllable and editable high-resolution dynamic 3D assets for use in movies, video games, or the metaverse. Is metaverse one word or two words? I thought it was one word. Many such applications require scalable approaches that can be run on high-resolution imagery in real time. This was one of the biggest kind of things that they talked about in the original 3D Gaussian paper that we read last week, where it's actually incredibly fast to render these because of the way that a GPU can do this kind of sorting process. It does this like tiled sorting that is actually very fast. So unlike a NERF, which is actually quite slow to render, these 3D Gaussians are very, very fast. Thus far, no approaches have been able to produce photorealistic reconstructions of arbitrary dynamic scenes with highly accurate tracks and appealing novel views. I don't know about this statement because it says nobody has been able to do photorealistic, not a very formal definition, arbitrary dynamic scenes, also not a very formal definition, highly accurate tracks. So all of these are subjective adjectives, right? It's like there isn't like a benchmark for highly accurate tracks. So all while being able to train quickly and rendered in real time. Okay, so good thing is good is basically what they're trying to tell us here. Return of the GANs. No, this is not a generative adversarial network at all, but you could take the ideas from generative adversarial networks and apply them to 3D Gaussians. Maybe you could do, right, the key idea behind a GAN is this idea of a generator and then a discriminator, and then putting them in this game such that the discriminator can basically feed gradients into the generator so it gets better and better over time at generating things. You can maybe do something with these 3D Gaussians where you're generating Gaussians and then using a discriminator to try to tell the difference between a 3D Gaussian generated image and a just normal real image, and then maybe improve it that way. I don't know. Lamb, hey, what if you use a lot of the 3D Gaussian fields to give multimodal models ground truth about physics and mechanical dynamics? Maybe that could enable better understanding. Maybe. It's not that the... Let me try to think about what I want to say. There isn't necessarily any physics and dynamics encoded into here, right? The physics is just literally just the trajectory and rotation of each of these Gaussians. I was more saying that you could, this type of more explicit representation of a 3D scene would be more useful if you were trying to do something with physics, but yeah, I don't know if they actually are going to look into that. In this paper, we present such an approach by simultaneously tackling the discriminative task of dynamic 3D scene reconstruction and the dense, non-rigid, long-term 6DoF scene tracking. So long-term here just refers to the duration of time, right? I think these are 4-second clips, and you're kind of tracking the motion of these little Gaussian 3D Gaussians over time. It's not super long-term though, right? It's not like we're talking about 4-hour footage. Like we're talking about 15-second clips. Non-rigid, dense, non-rigid scene tracking. While addressing the generative task of dynamic novel view synthesis, we formulate both of these tasks in an analysis by synthesis, i.e. we build a persistent dynamic scene representation of the moving scene that is consistent with all the input observations. Okay, so they're running this optimization process over the entire dynamic 3D scene, right? It's not like they're creating a static 3D Gaussian scene and then adding the time and dynamic components to it later. It seems like the optimization process runs over the entire duration of the time, from which tracking emerges as a product of correctly modeling the underlying scene with physically plausible, spatially consistent priors. So priors are kind of your assumptions. They're basically what you're starting with. A Gaussian is a pretty good prior. Spatial consistent, physically plausible spatial consistency priors. So this is basically just a fancy way of saying the not local rigidity constraint, probably maybe a couple other forms of regularization that are coming in as well. I think we'll continue to see the ideas behind GANs turn up to achieve repeatable novelty. Yeah, I saw a GAN paper, GAN XL or something like that. There was like a recent GAN paper that I saw that was basically a giant GAN. Like someone made a 1 billion parameter GAN. 1 billion parameter GAN. This one? Yeah, Giga GAN. Giga GAN. So here you have pictures of a generative adversarial network, which is very different from the diffusion models that you're used to seeing in most of your generative AI work. But this is a 1 billion parameter GAN, which is a monstrous size GAN. Looks like they're using CLIP as well. So I think that the data set is more important than the actual model architecture. So to me, it's like the quality is determined by the data set. So until someone creates a data set that is 10x bigger, or a CLIP model that is 10x bigger, trained on a 10x bigger, 100x bigger data set, I don't think the quality is ever going to like amaze us anymore, right? It's kind of like the same quality that you would expect out of the diffusion models nowadays. Okay, back to the paper. 3D Gaussian splatting has recently emerged as a promising approach to modeling 3D static scenes. So 3D Gaussian splatting, here they're already referencing that paper which literally came out. Yeah, this is like the paper that came out that we read last week, and this is literally 1 week from then. Has emerged as a promising approach to modeling 3D static scenes. It represents complex scenes as a combination of a large number of colored 3D Gaussians, which are then rendered into camera views via splatting-based rasterization. And the splatting is just kind of a fancy way of... Apparently splatting is something. I just want splatting. Yeah. So you take something that's 3D and you basically splat it onto 2D. Like in my brain, I keep thinking of the like Nickelodeon symbol where it just splats onto the 2D screen. Right? I think that's possibly the best mental image for what the fuck is a splat. The positions, sizes, rotation, color, and opacities of these Gaussians. So here's all the different parameters of a Gaussian, or one of these 3D Gaussians, right? It has some XYZ position, some XYZ size. The size is actually the covariance matrix, because the covariance defines kind of how diffuse versus how concentrated that Gaussian is. Rotation in space, the color of it and the opacity, which is the see-throughness, can be adjusted via differentiable rendering, and gradient-based differentiable rendering means you can take the chain rule and backpropagate through the rendering function, which means that you can eventually use these image reconstruction losses, and then gradient-based optimization, aka machine learning, multiple steps where you're using these gradients to improve the values of parameters, and the parameters that they're improving are these position, sizes, rotation, colors, and opacities, such that they represent the 3D scene given by a set of input images. In this paper, we extend this approach for modeling only static scenes to dynamic scenes, and this is kind of the big contribution of this paper. Our key insight is that we restrict all attributes of the Gaussians, such as their number, color, opacity, and size, to be the same over time, but let their position and orientation vary. Okay, so this is kind of the key prior or assumption is they're basically going to say, we're going to keep the Gaussians exactly the same, but then we're going to only change their position and orientation. And I think, as I said before, I think that works well for these type of scenes like this, where you have kind of static objects like humans and they're passing around a ball, but it's not going to work for everything, right? If you had a cloud of smoke and then you took your hand and you threw it through that cloud of smoke, that's a completely different beast, right? Because in that point, you would want to be changing the opacity of these Gaussians, potentially the size, right? Some of the Gaussians that represent the smoke would have to become more diffuse. There might be more Gaussians, less Gaussians. So I think this only works for the kind of scenes that they're showing you in this paper. This allows our Gaussians to be thought of as particle-based physical model of the world. Is it particle or is it a wave? Where oriented particles undergo rigid body transformations over time. Rigid body transformations is what you use in video games, right? It assumes that everything is a rigid body. Rigid means it's solid, it's tense, right? And it moves and it can hit things, and when you rotate it, all the things rotate, right? All the things move at the same time. There's kind of like this local rigidity, and then you can move and rotate that over time, like anywhere. In order to reconstruct such particles from raw camera imagery, we exploit the property that at any time they can be efficiently splatted onto any camera viewpoint. This is why you can basically get novel views, allowing them to be optimized with an image reconstruction loss. Particles allow us to operationalize physical priors over their movement that act as regularizers for the optimization. So here are all the different physical priors. We have a local rigidity prior, which is the one that they mention in the abstract, so probably the most important one. A local rotational similarity prior, so I don't exactly know what that'll be. And then a long-term local isometry prior. Isometry just means, iso means same, so isometric means it doesn't change as you move it, so the metric stays the same. So local isometry prior, maybe that kind of sounds like the local rigidity prior, but we'll see how that's different. These priors ensure that local neighborhoods of particles move approximately rigidly between time steps, and that nearby particles remain close by over all time steps. Okay, previous approaches to neural reconstruction of dynamic scenes can be seen as either Eulerian representations. So Euler space, right, is the just grid that we live in, right? Keep track of scene motion at fixed grid locations, or Lagrangian representations, where an observer follows a particular particle through space and time. Okay, so this is getting a little bit more fancy here, but the idea that the world can be broken into these particles, and that these particles are actually physical things, and that a particle can't just kind of disappear and then magically appear over here. It has to basically have a trajectory through space-time, right? So if you kind of dig a little bit deeper into physics, it actually tells you that our world might not even have this type of particle reality. There might be some kind of more complicated like situation going on, but for the macro world that we live in, right, at least the things in our scale of time and space, you can use these kind of particle priors, and you're pretty good usually. We fall in the latter, but in the contrast to prior point-based representations, we make use of oriented particles that allow for richer physical priors. So here they're talking about how normally when you are looking at for example, a point cloud, right? A point cloud that comes out of a laser sensor on the top of an autonomous vehicle, right? So this is a point cloud, for example. And like one thing that whenever you see a point cloud, right, you see these rings. You see how everything is kind of ordered in a weird kind of like circle, and it's like, why is that? It's because the sensor itself is rotating at the top of the car, right? So it's sending out a little laser pulse and it's rotating, and it rotates like that. So the laser pulses that it sends out are have that kind of cylindrical rotational kind of appearance to it. So that lets you know where the sensor was. So anytime you see these in point clouds, these kind of like circles, that's just telling you where the sensor was. So here in this picture of a house, right, we know that it seems like they probably set up a little laser scanner here, and then they took a bunch of points, and then they set one up here, and then they set one up here, and then they set one up here, and then they set one up here. So you can basically tell where the scanners were when they took this point cloud. But the reason I'm showing you a point cloud is that these points have only a position and a color, right? It's just XYZ position and then RGB color, and that's it. Versus here, they're using oriented particles. So now it's not just an XYZ point with a RGB color. It's an XYZ point with an RGB color, but it also has a opacity. It also has a size. It also has a rotation, right? It's oriented particles. Allow for richer physical priors that directly reconstruct the 6DoF motion of all 3D points, enabling a variety of downstream applications. I'm up early enough today. Hello, Emily. Hello, Christopher. Let's see. Author stated that Twitter X that he was working with fuzzy meatball Gaussians, but swapped to splat version for the fast CUDA when the 3D Gaussian splatting hit last week. Yeah, so I think I don't exactly know what he means by the fuzzy meatball, but I think it's about what are you using for your prior, right? So a point cloud is just XYZ RGB, but maybe a fuzzy meatball has like like some size, and then it also has kind of like little hairs that come out of it. I don't exactly know. But these are for this paper, the 3D Gaussians here, they're oriented particles that have some rotation and now have angular velocity and linear velocity as well. We perform experiments using synchronized multi-view video. So this is the camera geodesic dome that we were looking at. It looks like they have 480 cameras here in this paper where they describe this dome, but here they say they only use 27. So I don't know why they wouldn't use all of them. But you see how they have 27 training cameras and then 4 testing cameras. So they're going to have 4 cameras that they're never going to use it for training, but they're going to use those ground truth images as kind of a way to evaluate how good these dynamic Gaussians can reconstruct that exact image. So they're test train splitting their cameras. Our approach achieves a 28.7 peak signal to noise ratio on a dynamic novel view rendering while rendering at 850 frames per second. Holy shit. That's way faster than we'll ever need it. I think for VR headsets, for example, the headsets you have now are generally 60 frames per second. And 60 frames per second is pretty good, but if you were to like whip your head around really fast, you would see the 60 frames per second. So 120 frames per second is kind of the gold standard. At 120 frames per second, even if you're whipping your head around, you can still pretty much, it's very difficult to see the kind of like the world lag behind you. But maybe if you're like a human that has spider sensing, you're like you're the kind of like pinnacle of human frames per second, like maybe you can tell 120 frames per second, but 150 or 850 frames per second, that is beyond any human. There's no human that can tell the difference between 500 frames per second and 850 frames per second. So we're already beyond the frame rate that is going to matter for humans. Trained on 150 time steps with 27 training cameras, and each time step is only 2 hours on a single RTX 4090. So that's pretty good. This is a GPU that I have on actually this computer. So good to know that I can do this at home. Our approach results in a accurate metric, 3D dense, non-rigid, long-term scene tracking with an average L2 error of only 2.21 centimeters. Here they're talking about the distance between the actual thing and the tracked thing. So I don't know how they got the actual thing. I guess they probably, like maybe this baseball bat, right? Here's the L2 distance between that red line and that blue line. So maybe he's wearing kind of markers or trackers or something that allows him to get the actual position of that thing. Having an average of 1.57 normalized pixel error on 2D tracking, which is an order of magnitude better than previous state-of-the-art. Pretty good, but this is also based on results that they got in this camera geodesic dome, right? So if you had little shaky video from a iPhone, maybe you don't get this level of quality when it comes to the tracking. Our method is also able to track the rotation of every 3D point in space, enabling full 6DoF dense scene tracking. A remarkable feature of our approach is that tracking arises exclusively from the process of rendering per-frame images. Right? You get it for free, is kind of what they were saying in the abstract. No optical flow, pose skeletons, or any form of correspondence information is given as input. There is correspondence information, right? Correspondence information is coming in through the fact that you know where all these cameras are, right? And that's where it's coming in. So I still feel like they're being a little cheeky here and making it seem like it's this magical thing, but I think a lot of these results are coming from the fact that they're filming this in this perfect dome with these perfectly calibrated cameras. Dynamic 3D Gaussians are naturally amenable to a number of creative scene editing techniques, such as propagating edits over all time steps, adding or removing dynamic objects to a scene, having cameras follow the scene elements. So kind of what we were referring to earlier, they're not doing any lighting or relighting. That would have been something cool to see. They probably will work on that in the future, or somebody will, and enable real-time rendering. Okay, related work. So now they're going to talk about what their work is related to. I read somewhere they aim to release the code and stuff in October. They seem to use quaternions. You're going to love this. I love quaternions. They're just really, they're so cool, right? The fact that you take something which, there's different ways of representing rotations, right? You have Euler angles, which are 3 numbers, and then you have rotation matrices, which are 3 by 3, right? So 9 numbers. And the 3 numbers, the 3 Euler angles, are not good enough. They're just not quite good enough. You have these kind of gimbal lock situations. Where basically, if you're only using Euler angles, you can end up in a situation where you don't actually know. It's under parameterized, I guess is the way to think about it. And then a rotation matrix is over parameterized, right? So in a rotation matrix, you're keeping track of 9 numbers, which represent the rotation of a thing, but that is over parameterized. You don't need all of those numbers. And the fact that quaternion is exactly 4 numbers, which is just 1 more than the Euler angles, and that quaternions perfectly represent all rotations in 3D space, I just think there's some kind of like beautiful math to that, right? That 3 is not enough, 9 is too many, but 4 is just perfect. And that's kind of why I like quaternions. I got the bait. We'll be hyped till the real world test comes. Yeah, I'm really curious to see how the research community runs with this 3D Gaussian stuff. It seems to be moving really quickly, but we'll see. Related work. Interested in solving the combination of novel view synthesis and dynamic scenes, long-term point tracking, and dynamic reconstruction. So dynamic novel view synthesis. General field of novel view synthesis exploded in popularity with the release of NeRFs. NeRFs have been a large number of dynamic NeRF papers. Okay, so people trying to basically take these 3D radiance field and make them 4D. So add the time element or the dynamicness of the scene. Most of these use monocular video as input. Monocular just means one eye, monoocular, single camera. Whereas we focused on using multi-camera capture. Typically, multi-camera capture is how you're getting this correspondence information, BTW. Typically, these methods belong to one of the following 5 categories: methods that fit a separate representation per time step and cannot model correspondence over time; methods that represent the scene using a Eulerian representation on a 4D space-time grid, often with various grid decompositions for efficiency, such as planar decomposition or hash functions. So these are different types of nerfs that are trying to add the time element in different ways that people have added them. Methods that represent the 3D scene in a canonical time step and use deformation field to warp this. Such methods usually naturally result in one-directional backwards correspondences between each frame and the reference frame, but by default not the forward correspondences which are required to generate correspondences between any 2 time steps. I feel like I recall seeing a diffusion paper that we read where they kind of had a similar kind of thing where they were trying to do generate videos rather than individual pictures, and then they had this kind of correspondence between subsequent frames and then a correspondence between kind of a key frame and the current frame. So managing and adding these regularizations to have the right correspondences between local things in time, so frames that are right next to each other, and then more global things in time, so frames that are further apart, it's still pretty difficult, and there doesn't really seem to be an accepted way to do it. And every single paper that I've read, it just kind of feels like a bag of hacks, so we're not quite there yet. A number of methods specifically parameterize their warp fields in a way that is easily invertible, such as linear blend skinning or reversible neural networks, or in order... What the fuck is a reversible neural network? Oh, is that the one that... I think we might have actually read that. While this often works quite well, requiring a single canonical view for the scene greatly restricts the dynamic representation ability. Let me actually move this fucking monitor because I feel like I'm speaking sideways. Template-guided methods which model dynamic scenes in restricted environments where a motion can be modeled at a predefined template in a set of human pose skeleton transformations. So, pose detection. I wonder if this type of stuff is going to go away too, but here is a human pose skeleton-based model. This is actually a very simple one. Generally, the number of points and edges are a little bit more complicated. Now you see here you have the face as well, so the face and the ears, but then you also have hands now. The hands are the most complicated because they're very small and very intricate, and the amount of weirdness that you can get in a hand is very high. So hands are by far the hardest thing to track. Maybe it makes sense that they're also the hardest thing to generate with an image generator. Point-based methods, which compare all the above, hold the most promise for representing dynamic scenes in a way where accurate correspondences over time can emerge due to their natural Lagrangian representation. However, these haven't achieved as much attention because point-based rendering approaches haven't worked as well as the multi-layer perceptron or grid-based approaches. So this is a point-based approach, which is, there's this kind of continuum between like kind of more explicit representations of a scene and then more implicit representations of a scene, right? So as soon as you have a grid, that seems more explicit, right? You're saying, okay, I'm breaking down my world into this grid, and then at each kind of voxel within this grid, there's going to be something, versus a true nerf that is just a single little tiny neural net. That's kind of the most implicit representation. So there's a smooth, maybe not smooth, but there's kind of this continuum between how explicit versus implicit is the representation of your scene, and each of them have their own kind of advantages, disadvantages. We build our dynamic 3D Gaussian renderer upon this static renderer, which is currently state-of-the-art static scene reconstruction. Other than rendering accuracy, modeling the dynamic world with Gaussians has a distinct advantage over the points that Gaussians have a notion of rotation, right? So they have an orientation. Let's get a picture of a 2D Gaussian in here. Oh, 2D Gaussian. What the fuck just happened here? Converse. What is this? I just want a 2D Gaussian. Show me a 2D Gaussian. This is a 2D Gaussian. So you can see how 2D Gaussian here, it's shown with the same variance in X and Y, but normally they're going to be like this. You know, they're going to have they're going to look more like an ellipsoid, and then you can imagine, okay, what about the 3D version of this? It's basically going to look like a little sphere cylinder looking thing. Actually, what if we type 3D Gaussian in here? Does it come up? This is not a 3D Gaussian. This is a 3D Gaussian. This is what it actually looks like. It's like a little elongated little sphere. Ellipsoid. What is the 3D version of an ellipse? Ellipsoid? Am I correct in that? Long-term point tracking. Traditional video tracking algorithms have been focused on tracking whole objects, such as bounding boxes or segmentation masks. Tracking dense scene points, but only between 2 time steps, optical flow and scene flow. Recently, a number of approaches have started tackling the task of long-term dense point tracking, and even then, even the videos or the papers that we've read kind of on this type of tracking problem, they call it long-term, but like we're still talking about like 10-second clips, 30-second clips, right? We're still a far ways away from hours or days of tracking, you know, where you're tracking the same thing over hours and hours and hours of footage, where every single pixel in a video needs to be tracked across every video frame. We extend this long-range tracking task to 3D and evaluate it in a multi-camera capture setup. Most of these prior approaches are deep learning and work by being trained on a large data set of ground truth point tracks, often using synthetic training data. Yeah, a lot of these NeRFs use synthetic training data because they need to know the exact position of the cameras, but you don't really need to do that if you have one of these giant camera domes, right? You get that for free. Also fits dynamic radiance field representations using test time optimization for the purpose of long-term tracking. They focus on monocular video while we focus on multi-camera capture. These two they're making this sound like it's more different than it really is. Like monocular video, right? Let's say you have a cell phone camera with just one camera, right? It's monocular and you're taking a video, so you're moving over time. The way that most people treat that is as a kind of a multi-camera capture, right? If you think about it, let's go to images. I'm trying to find a specific picture here, but you're taking a point, you're taking a camera and you're moving it, and that's kind of the same as having multiple cameras, right? So if you have a camera here and then you move it over here, isn't that kind of the same thing as having 2 cameras? So at the end of the day, what you really want is to see the scene from multiple different viewpoints. So you either have multiple cameras that are all looking at it from a different position, or you have one camera that's moving to different positions. So even though it sounds like there's a huge difference between monocular video and multi-camera capture, at the end of the day, it's kind of the same thing, right? You're just having pictures, a series of pictures of something, and they need to be from different places. So you can't just have the camera sitting there statically. So either you have many cameras that are in different places, or you have one camera that's moving. While they produce a pseudo 3D representation. However, the largest and most significant difference between our method and OmniMotion is that they require dense optical flow input between every pair of time steps as optimization target, which is incredibly expensive as it scales with the number of frames squared. Okay, so if you have to calculate optical flow between every pair of time steps, it's going to be incredibly expensive. Our method takes no correspondences at all as input, and tracking emerges from fitting a persistent representation to the input frames along with physically based priors. So you don't need to have an explicit correspondence in the form of optical flow or a human pose skeleton or any of that. It's kind of implicit in the optimization process, and the fact that you have these multiple cameras, you're just going to, the correspondence information is still there. It's just not, you don't need to explicitly build it and then feed it in. Dynamic reconstruction. In addition to the radiance field-based approaches, a number of other approaches have tackled the task of dynamic reconstruction. Such approaches either rely on the presence of accurate depth cameras, and there is no such thing as a fucking accurate depth camera. I'll tell you that right now, as someone who's like dealt with this in the real world. All of them suck. The laser ones suck. The structured light ones suck. Any kind of ultrasound sucks. Like, all the ways that we have of getting depth have issues. So the only way you're going to have an accurate depth camera is if you're using a synthetic scene, like a game engine, and you can get perfect depth from that. But depth in the real world is, especially accurate depth, is a pipe dream. We're never going to get it. Assume ground truth object point clouds as input or heavily specific to certain domains. The closest approach to ours is 14, which also predicts long-term 3D point tracks and also uses Panoptic Studio data for evaluation. However, this approach requires 480 input cameras. We only use 27, which is the full amount. Okay, so this is actually probably their previous paper. And that's how academia works. You got to reference your previous papers and the papers of all your buddies and everybody else at your institution in the related work section so that they get some citations and you can keep the money flowing. All right, but now that we're done with the related work section, let's get into this method section here where they're going to basically talk about their technique and what they're doing in this paper. No correspondence means camera angle. No, correspondence is the notion that one thing from one picture corresponds to another thing from another picture. It could be a specific point, right? Maybe if you're doing I lost this one. No. So it can be a specific point, such as this elbow in this skeleton representation is here in this frame and here in this frame. It can be a little area of pixels, right? It can be a bounding box from this frame to this frame. Correspondence just means that you're basically saying this thing in this frame is the same as this thing in this frame. And there's a lot of different ways to have an explicit kind of correspondence. They point out a bunch of them here: human pose skeletons, optical flows, bounding boxes, but they don't need that explicit representation. I'm more saying that it's implicit because the information is there, right? The fact that you have multiple cameras that are all looking at the thing and you know where those cameras are, that means that the information is there, as in like it's available, right? The optimization process is going to find it. That pattern is there to be found, right? It's not like you have just a single monocular camera that's staring at a thing. It doesn't matter if you gave that to an AGI system. The AGI system is not going to know whether that's a big object or a small object that's close to you, or a big object that's far away from you. But as soon as you have two cameras, you give that to an AGI, it can figure it out, right? Eventually it'll find out, okay, actually this is a big thing that's far away from me or whatever, right? I don't know. Hopefully that makes sense, Christopher. I don't know if I answered your question. Okay, given a set of images from different timestamps and different cameras. Okay, so we have a set of images, ITC. I think T refers to time and C probably refers to cameras. Let's make this, I think blue is the color for numbers and then green is the color for math definitions. Along with each camera's respective intrinsic, KC, and extrinsic matrices. So, if you're not a computer vision person, these are very important matrices. And basically what these matrices represent are the information of that camera. So an extrinsic camera matrix tells you where the camera is in space. It's basically telling you, here is where my camera is in 3D space. That's what the extrinsic matrix is telling you. The intrinsic camera matrix is basically telling you what are the kind of properties of this camera in terms of like kind of the way that it warps and looks at things. So, let's see, intrinsic camera matrix. So it's kind of like if you have a camera that has a weird fisheye effect, that's all going to be present in the intrinsic parameters. So here you go. Here's your intrinsic parameters. You can see how you have kind of some notions of like the focal length in here. Focal length, the distortions, like those are all going to be properties of the intrinsic camera matrix. The extrinsic camera matrix, so you see here, is just a rotation and a translation. It's just basically, here's where my camera is in 3D space. So this is hard, like this is already, they're starting from very strong information, right? If I'm just going and filming in my backyard with an iPhone, I might know what the intrinsic camera matrix is, but I sure as hell don't know what the extrinsic camera matrix is, right? I can approximate it with something like Colmap, right? Or some kind of other stitching kind of thing, but like I'm not going to know that. And I'm certainly not going to know that to the accuracy that you're going to know that if you have one of these domes. So the fact that they have the extrinsic camera matrix for every single one of these cameras is a pretty strong starting point. I think it's very difficult to replicate in the real world. Our approach reconstructs the dynamic 3D scene S observed by these cameras in a temporally persistent manner. This reconstruction is performed via test time optimization, and no further training data other than the test scene is used. Yeah, so it's not... One thing about these 3D Gaussians is that it's a machine learning process in that you're using gradient descent to learn the values of these Gaussian parameters, but it's not like a neural network, right? It's not a neural network where you're feeding it maybe in a supervised learning context. You're feeding it, here's an image, and then here's the output, here's another image, here's the output, and then largely the quality of the representation that neural net builds is based on your training data. This is not that kind of machine learning. So you don't actually need training data in the sense that you think of training data normally in a machine learning world. Here, the training data is just the set of images, and that's what's being used to optimize the values for these Gaussians, the properties for these Gaussians. The reconstruction is performed temporally online. One time step of the scene is reconstructed at a time, with each one being initialized using the previous scene's time steps representation. Okay, so this is good information to know, is that you're basically building this one step at a time. The first time step acts as an initialization for our scene where we optimize all properties. Okay, so this is kind of the same notion of like the keyframe. So the first time step, because it's so important, because you're initializing every subsequent time step based on the previous one, that first one is very important. So you basically want to probably spend more compute, more time, maybe more complicated regularizers on that first time step, just because any mistake there is going to propagate all the way down. Because they don't have a neural net, they have 850 frames per second. Yeah, that's why it renders so quickly, is because you don't have that neural net. The reason nerfs are so slow is that you have to perform inference on a neural net for every single one of these little black dots, right? And every single pixel in your image might have 10 of these little ray samples, right? So even if your little neural net here is tiny, right? Even if it's like a 3-layer multi-layer perceptron, which is kind of what they're showing here, right? 3 little layer neural net. Even if it's tiny, you're performing thousands and thousands and thousands of these inferences. So that's why nerfs are very slow. But here, there's no neural net, there's no inference. You just have these 3D Gaussians and they're moving, so all you got to do is just keep track of them. And computers that we have nowadays are pretty good at that. And then fix all of the subsequent time steps except those defining the motion. Each time step is trained via gradient-based optimization using a differentiable renderer. The differentiable renderer, again, is key because you're going to be using a reconstruction loss, and you need to be able to push that reconstruction loss past the renderer into the actual 3D Gaussians to render the scene at each time step into each of the training cameras. Okay, so we have the rendering I hat TC. So ITC is the actual image, I hat TC is the reconstructed image, and the reconstructed image is going through this rendering function. The rendering function is taking in the dynamic scene S at some time step T. It's taking in KC, which is the intrinsic camera matrix for the specific camera that you want to render from, and the extrinsic camera matrix for that specific camera. Then compared to the input images, and the parameters of S are iteratively updated using automatic differentiation in order to decrease the error. And this is basically the learning process right here. After convergence, the representation S of T is a 3D reconstruction of the scene given by each of the training cameras. There you go. So what is S of T going to actually be? It's going to be basically this giant collection of 3D Gaussians that have some position and orientation. By choosing a suitable representation for S and applying physically based regularization losses during optimization, we can ensure that all of these S of T are temporally consistent with one another. Okay, so maybe each individual Gaussian in one S of T corresponds to the same Gaussian in the next S of T. So it's not a set of things. So in for example, Python. In Python, there's a difference between what is called a list and a set, right? A set is unordered versus a list is ordered. So even though set means something different in math, you could think of this S of t, the order is going to matter, right? You're going to have a specific one-to-one correspondence. You need to maintain that index, right? That Gaussian at index 452 is going to be the same Gaussian at index 452 at the next time step. There exists a one-to-one correspondence between every 3D point and every time step, along with their corresponding changes in 3D rotation. In this way, tracking emerges from persistent dynamic view synthesis. And this is what they mean, is that you did not need to give it this correspondence explicitly. You just get it, right? So you just get this one-to-one correspondence. So if you needed that for some other reason, now it's very convenient. Now you just have it for free. Hupo, do I know about demo scene? They cannot handle anything new that is not in the initial state. You are correct, John. If there's a new object that appears, it is not going to be possible to, like, if halfway through this scene, I threw something at this person, no Gaussians would exist to represent that, so it wouldn't be able to handle that. So yeah, it is limited. I don't know what demo scene is. Let me look this up. What is demo scene? European phenomenon, competition-oriented subculture with groups and individuals competing against each other in technical and artistic excellence. Self-contained computer programs that produce audiovisual representations. Dude, what is this? I mean, this doesn't... So, first thing when I see this, absolutely badass looking. Second thing when I see this, these aren't the same. So, it's not like there was a event organizer and they gave them each their own computer. These are all everyone's personal computers. So, everyone in this picture brought their own computer. And these are like... This is back in the day with CRT monitors. So, everyone brought this big cardboard box with a CRT monitor and like a fucking Intel Pentium. This is badass, dude. I like this. Pretty cool. They call me Ken. Are you part of that community? Dynamic 3D Gaussian. Our dynamic scene representation S is parameterized by a set of dynamic 3D Gaussians, each of which has the following parameters. A 3D center for each time step, so this is the position. You have the rotation, and this is your quaternion, right? You have X, Y, Z, and then that extra parameter that you need, that extra quaternion number, which allows you to perfectly represent all rotations. It's up your alley. Yeah, for real. I mean, I need to go to that. You know, if only I could leave my family behind, then I could go to these cool computer vision competitions. The 3D size and standard deviations. So this is basically the kind of the variance of the Gaussian, but in the original 3D Gaussian paper, they kind of treat these Gaussians as ellipsoids. So the radius of the ellipsoid in each dimension is kind of what they're referring to here. A color, so RGB, the entire 3D Gaussian is just a single color. The opacity logit and the background logit. Logit just means it's between 0 and 1. So you might have heard the term logit in a classification model, right, where the logit is the very last layer, right, and it's supposed to represent basically the probability of this image being a cat or this image being a dog for each class. But here it's basically just going to represent the opacity. So I guess something with, if the opacity logit is 0, it means it's perfectly see-through, and then it's probably going to get pruned. If the opacity logit is 1, it means it's perfectly not see-through. And then a background logit. Okay, so background logit makes it sound like there's probably this notion of foreground background, which isn't great. You know, I generally don't like these kind of explicit foreground background notions. Like, I feel like that's just not, we need to get rid of this. Like, I feel like the technique of, like, when it's 2030 and we have the perfect representation of 3D, I feel like it's not going to have some notion of background foreground. I feel like that's that's just a crutch that we're using nowadays. This gives a total of 7t plus 8. So if you count all of these up, you basically get 7t plus 8 parameters for each Gaussian, which isn't too bad, right? And you can probably use slightly different data types for some of these, right? The color, you could use uint8, which is a very small data type for the color. For these rotations and centers and sizes, you probably want to use something like a float, maybe float 16, maybe b float 16. Does that even make any sense in this context? Scenes are represented to between 200 to 300,000 Gaussians, of which 10 to 30 to 100,000 are usually not part of the static background. Okay, so 300K individual little Gaussians and maybe 100K to represent the actual foreground. So most of the Gaussians are actually just the background. Kind of interesting. While the code contains the ability to present view-dependent color using spherical harmonics, we turn this off for simplicity. Yeah, so this is view-dependent color means that depending on where you're looking at, the color of that Gaussian is going to change. And that is important if you want to do the relighting, right? So I was talking shit on them earlier because these compositional scenes don't have any lighting, but that's where you would put it in. Basically, if you wanted to add relighting to these compositional scenes, you would put it in through the spherical harmonics, right? Which would allow you to say, okay, well, this Gaussian here, when I look at it from this point of view, the light would make it look like this. And when I look at it from this other point of view, the light is going to make it look like that, and so on. But here they're just going to get rid of it just because it's just a bunch of extra crap that they don't really care about for this paper. The amount of Gaussians is a hyperparameter, right? Yes, you are correct. Background logit is an index of the position. Probably not. The logit means it's in between 0 and 1, so I think it's probably just 0 or 1. It's just like a binary. It's basically like, is it background or is it foreground? That would be my guess, but we don't know yet. Each Gaussian can be thought of as softly representing an area of 3D physical space, keyword soft there, which is occupied by a solid matter. Each Gaussian influences a point in physical 3D space according to the standard unnormalized Gaussian equation weighted by its opacity. So unnormalized here refers to the fact that you have your Gaussian equation here, your exponent of the thing, but there's no term here to normalize it. So if you have a Gaussian equation, this is the equation for a Gaussian function. This is the Gaussian equation here, and this term here normalizes it. So by dividing this by this, you make sure that the area under this curve is exactly 1, but here it's unnormalized, so they don't have that part at the front. So let's see. We have sigmoid of OI, so they're putting this opacity logit through the sigmoid to make it between 0 and 1. Here you have your P. What is P? P is, where are they telling P? Where is P? So we don't know what this P is yet. The mu, I guess, is probably the XYZ. So you have a mu for a specific I, which is the index, and then index of that particular Gaussian, and then you have a specific time step T. Here you have the covariance matrix for that specific Gaussian, which is basically just the sizes here, the standard deviations, right, in a diagonal matrix, where mu it equals, okay, so here's the center, mu is the center at each time step t, and sigma it is RIT SI transpose RIT transpose, which is the covariance matrix, which is basically these three numbers here, the standard deviations for each of the dimensions. By combining the scaling component SI and the rotational component RI. So this is a trick that they did in the original paper as well. So rather than saying, okay, well, we have some Gaussian and this Gaussian has some covariance matrix that represents basically the variance for each of the dimensions. They're treating these Gaussians as these little ellipsoids, right? These little like cookies, maybe, I don't know, like round cookie things, right? And they're saying, okay, well, rather than dealing with this covariance matrix, let's instead just pretend that the covariance matrix, you can basically create it by rotating and scaling, right? Scaling means making things bigger, smaller, and then rotating means taking that little like Gaussian and rotating it, right? So they're just representing the covariance in as rotation and scaling matrices. Where Q2R is the formula for constructing a rotation matrix from a quaternion. So the only bad thing about quaternions is that you can't use them easily. You can take quaternions and rotate other quaternions with those quaternions, but if you want to take a vector of points and then rotate that vector of points by a quaternion, you got to turn it into a rotation matrix. So that's part of the problem. That's one of the reasons they're annoying, but I still think that they're better than pretty much everything else. Each Gaussian influence is both inherently local, being able to represent a small area of space, while also theoretically having infinite extent, such that the gradients can flow to them even from a long distance. Okay, so interesting. So they're saying that, right, a Gaussian technically is defined infinitely. So like it seems like it just drops off, but it's not exactly zero here, right? It's hard to do with a 2D Gaussian, but there is some amount of probability mass here, and that means that if you're pushing gradients and saying, okay, well, this pixel over here should have this particular appearance, maybe a Gaussian that seems like it's initially kind of far away actually has a very long tail that goes right through that point, so you can push a little tiny bit of gradient into that Gaussian that seems like it's further away from the pixel that you actually are pushing that reconstruction loss to. It's crucial for gradient-based tracking by differentiable rendering, as Gaussians which may currently be in the wrong 3D location need to get gradients pushing them towards moving to the correct 3D location through the differentiable renderer. So here they're talking about, it's not the appearance, the gradients are more about the location. So it's not that those gradients are changing this RGB value, the gradients are changing the center, this XYZ, and then the rotation. Softness of this Gaussian representation also means that Gaussians typically need to significantly overlap in order to represent a physically solid object. As well as physical density, each Gaussian contributes its own color to each of the 3D points it influences. Okay. By fixing the size, opacity, and color of the Gaussians across time, which is another kind of strong assumption. You know, there's a lot of strong assumptions in this paper. The extrinsic matrices being known for every single camera, that's pretty strong. The size, opacity, and color of the Gaussians staying exactly the same, also pretty strong. But if you didn't have these strong assumptions, you just couldn't do anything. So they're just doing the best they can. Each Gaussian should represent the same physical aspect of space, even as the space dynamically moves through time. To represent this motion, each Gaussian has a center location and a rotation that can move with time, enabling full, dense, non-rigid 6DoF tracking of the whole scene. We visualize the trajectories of these Gaussians, the locations, and the change in rotation over time. Iterative rotation tracking. Left-facing colored vectors are attached to 3% of the Gaussians in the first frame, second, and third panels. Okay, so this one here, this is 6DoF, so you can see how the rotation changes. So if you look at the Gaussians that are, for example, on this baseball bat, right, that's telling you the rotation, so you can see how here's you have the rotation of that Gaussian, it's moving. So it's not like you have the same 3D Gaussian that's just kind of like staying at the same rotation and just moving like this in XYZ. It's like the almost like the Gaussian is correctly stuck to the object and giving you that full 6DoF tracking. Okay, differentiable rendering via Gaussian 3D splatting. In order to optimize the parameters of our Gaussian to represent the scene, we need to render the Gaussians into images in a differentiable manner, right? Need to be differentiable, or else you're not going to be able to chain roll and you're not going to be able to push gradients. In this work, we use the differentiable 3D Gaussian renderer from 17 and extend its use to dynamic scenes. This is, the paper that we read last week, and basically what it is this tile-based renderer that uses like a sorting. So it's kind of like for every tile in an image where the image is broken up into these little tiles, very similar to a vision transformer actually. In vision transformers, they call them patches, but here it's tiles. And for every tile, you can basically say how many of these Gaussians overlap with this tile in 2D, and then I'm going to sort those Gaussians based on the distance to the camera, and then I'm going to basically render them. I think in the paper they say you can render them from the back and from the front simultaneously, so you kind of like, and then meet in the middle. This works by splatting 3D Gaussians into the image plane, so 3D into 2D, splatting into the image plane, aka making a 3D thing a 2D, by approximating the projection of the integral of the influence function f across the depth dimension of the 3D Gaussian into a 2D Gaussian influence function in pixel coordinates. I don't know why they call it influence function. That makes it sound so much more fancy than it is, but like each Gaussian influence f is just literally this. And it's just basically how much is this Gaussian contributing to the final appearance of this pixel, right? So the color of each pixel is influenced by a bunch of 3D Gaussians. So I don't know, I don't like the word influence. That sounds a little weird, but that's what it's doing. The center of the Gaussian is splatted using the standard point rendering formula. So here you have your intrinsic camera matrix making a comeback. You have your extrinsic camera matrix. You see how they're using the extrinsic camera matrix to change, or you multiply it by the extrinsic camera matrix is a 3x3. You multiply it by this point mu, which is also 3x3. You get another 3x3. That's the basically translated rotated point, where the 3D Gaussian centered U is projected into a 2D image by multiplication with the world to camera extrinsic matrix E, Z normalization, and multiplication by the intrinsic projection matrix K. Okay. And that gives you the center of that 3D Gaussian, but in 2D. So we've basically taken that 3D Gaussian and projected it into 2D. So this here, two-dimensional, right? And that, let's see if we go here. You see this intrinsic camera matrix? See how it's 3x4? Where is it? Yeah, right here. UV. UV is the coordinates of the actual 2D image coordinates, right? So when you multiply a 3D vector x, y, z by this intrinsic matrix here, you end up getting U and V, so you end up getting 2. Here this is a little bit confusing because they add this 001 here at the bottom just so you can the extrinsic matrix here is 3x4 because it has both the translation component and the rotation matrix combined, right? But ultimately, the 2D coordinates are coming out of here. So U and V are in like pixel coordinates. Not exactly pixel coordinates. They're in camera coordinates. That's why you have to normalize it, right? Because eventually it's just going to be a number between 0 and 1, right? And then you need to turn it into actual pixels. Okay. The 3D covariance matrix is splatted into 2D. Why do they use the sigmoid if the logit is already between 0 and 1? So the logit is not necessarily between 0 and 1. You're interpreting it as between 0 and 1. The sigmoid makes it between 0 and 1. Here. Right? The logit is some number that's going to get squashed by the sigmoid to be between 0 and 1. But I don't really know the exact reason, so let me tell you here. Why, if a logit is already between, it's not, is between, this is not correct, but we'll see if we get corrected. Then why do we need to take the sigmoid? I think the answer is log it is not already between 0 and 1, yeah. You might be confusing the output of the logistic function with the log it itself. The log it is the inverse of the logistic sigmoid function. Yeah, so the values at the last layer of a classification model are called the logits, and those are not between 0 and 1, but you take the sigmoid of them and then they become between 0 and 1. Here you go, there's your answer. Hopefully that didn't confuse you even more, Chris. Okay, so what were we talking about here? The 3D covariance matrix here, your covariance matrix, is projected into 2D using this. So here you have your extrinsic camera matrix again, which is going to now convert these this covariance, which is effectively just the standard deviation, aka the size of that ellipsoid, and then the rotation, right? Here the covariance matrix is basically these R's and multiplied with these S's. The S is the scale, which is the standard deviation, and then the rotation here is the quaternion, converted to a rotation matrix. And then you have J is the Jacobian of the point projection formula. The Jacobian, it's hard to describe Jacobians, but it's basically like the partial derivatives for a linear mapping. Let me see if I can get a better description of that. The Jacobian matrix. Here you go. So let's say you had some function f that mapped from n to m, right? Then the Jacobian would be df1, dx1, all the way to df1, dx2, df2, df1, dx3, all the way to dxn, and then dfm all the way down to dx. I think I said that incorrectly, but largely it's basically just this giant matrix of partial derivatives here. Point projection formula above. So here they're taking the partial derivative of this 2D point projection formula here with respect to the point itself. The influence function f can now be evaluated in 2D for each pixel for each Gaussian. Okay, so you can get the total amount of influence or the contribution of that specific Gaussian to that specific pixel for any pixel and any Gaussian. The influence of all Gaussians on this pixel can be combined by sorting the Gaussians in depth order and performing front-to-back volume rendering using the max volume rendering formula, using the same as used in NERF. So this is the sorting that they talked about in the first paper that we read. The final rendered color, which is actually what's going in each pixel, a single RGB value, is a weighted sum over the colors of each Gaussian. So here's your Gaussian influence function, which is specific to a specific pixel and for some specific Gaussian. And you're kind of basically adding them up. Here it sounds like you're kind of multiplying them because there's this opacity here, but you're multiplying them up and then summing them, summing all those colors, right? So something that's see-through but at the top of the stack is going to contribute more than something that is not see-through but all the way at the bottom of the stack, which kind of makes sense. If they are not using spherical harmonics to encode the color, does it mean that the color is not depending on the viewing angle? Yes, you are correct, Mauro. They're not. It's not, and I think they just didn't include it just for simplicity, but they're probably working on it right now. Rotated and scaled ellipsoids create a mental image for me of these Gaussians as single-cell amoeba swimming around. Yeah, that's basically what's happening, John, except I think amoebas, when they move around, they kind of distort, right? Amoebas kind of get skinnier and then fatter, and then they're kind of like almost undulating. But in this case, the Gaussians are fixed, so they're not moving. The scale stays constant and the color stays constant. So the only thing that's changing is the rotation and the position. weighted sum of the colors of each Gaussian, weighted by the Gaussian's influence on that pixel. The equivalent of the formula Fi in 3D, except the 3D means and covariance matrices are replaced with the 2D splatted versions and downweighted by an occlusion term or transmittance or opacity, taking into account the effect of all Gaussians in front of the current Gaussian. So this also means that there's probably optimization here that you could do where at some point you don't need to calculate the influence for Gaussians that are kind of like past a certain point of opacity. You know, it's like you don't need to be calculating the influence of a Gaussian that is behind this person, right? The Gaussian for the part of this background here that is behind him, you could save compute on that, but maybe that just adds more complexity and you don't actually save that much. So the implementation uses a number of graphics and CUDA optimization techniques. Here they're referring to the fact that this procedure here, this sorting and then this inference and then this rendering, or not inference, influence, you can write it as a CUDA kernel, which is the actual code that runs on your GPU, and you can write it in a way that's actually very optimal, right? And the optimality of a CUDA kernel comes down to like how many times do you have to change what's in the memory? How many times do you have to go get some other group of numbers, some other tensor of numbers and bring them in and take them out and bring them in and cache something? So just through the magic of science, it turns out that this particular way of splatting and calculating the final color of pixels actually turns out to be quite quick on a GPU, which shouldn't be surprising because GPUs were literally designed to do that, right? They were designed to render the appearance of pixels based on lighting for video games, right? So it kind of makes sense that they would also work well for this Gaussian splatting. Okay. Physically based priors. So actually, you know what? One thing that, let's say you have, what is a 4K resolution? 4K resolution is 3840 by 2160 pixels. So if we do 3840 times 2160, what do we get? We get 808,294,000. So maybe it's not as crazy as I think it is, right? So whenever they say, okay, well, each of these Gaussians is around 300,000 points, right? Where is it? Oh my God, I can't see it. But they say that it's 200 to 300,000 Gaussians. You know, compared to the number of pixels in a 4K image, that's really not that much. So it kind of makes sense that it's actually really fast because 300,000 is an order of magnitude less than this, and you can run like games on a modern GPU at 4K resolution, 60 frames per second, right? So 850 frames per second for 300,000 Gaussians kind of makes sense. A Gaussian is obviously more than a pixel. A pixel is just 3 numbers. These Gaussians are a little bit more than that. They're basically kind of 15 numbers, but the back of the envelope math kind of checks out for this 850 frames per second number that they keep talking about here. We find that just fixing the color, opacity, and size of Gaussians is not enough on its own to generate long-term persistent tracks, especially across areas of the scene where there is a large area of near uniform color. Yeah, this is a huge problem in like so many other things in computer vision, these large areas of near uniform color. If you've ever done like stereo disparity or monocular depth or anything like that, these always have issues. In such a situation, the Gaussians move freely around the area of similar color as there is no restriction on them doing so. Okay, so basically one of the things that they have, you know, it's kind of hard. You're trying to over time, you're saying these little Gaussians move around, but the Gaussian that is here can just move over here, and the reconstruction loss is not really going to penalize it that much for doing that because it's kind of looks the same, right? It's all just kind of this white texture, so, or lack of texture. So this is probably how they're going to introduce the constraints in order to prevent that kind of motion of the Gaussians. Since we are trying to model physical moving, it makes sense to look to non-rigid physical modeling for inspiration on how to regularize the optimization procedure to be physically plausible and give correct long-term tracking results. We introduce 3 regularization losses: short-term local rigidity, L rigid, local rotation similarity, L rot, and then a long-term local isometry loss. The most important of these is the local rigidity loss, this one here. So you have mu j t minus 1 minus mu I t minus 1. So j and I are probably 2 different Gaussians. So the difference between the mean of these 2 Gaussians, right? So it's like basically the distance between these 2 Gaussians minus the rotation matrix of I. So the rotation matrix for Gaussian I times the vector from. So what's happening here is you're basically saying the distance between these 2 Gaussians here, j and I, of which the j is the center, mu j is the center of the j1th at time t, and then mu I is the center of the ith one at time t. You're saying that distance between them, right, this vector here, should ideally not change too much, right? This states that for each Gaussian I, so this is L rigid, nearby Gaussians j should move in a way that follows the rigid body transform of the coordinate system of I between time steps. So if you have this little Gaussian, right, and it has some rotation and it has some relationship to the Gaussian next to it, right, when that rotation matrix changes that, like this rotation matrix does that, then that Gaussian there should also rotate, right? The distance between those, it shouldn't just rotate the same. It should basically follow this rigid body transform, right? You see that? How like there's a difference there. It's not that you want your 2 Gaussians to both rotate the same way. You want the rotation to be basically relative to the local rigid body transform of this one. And if you do that for all the Gaussians, then you get this kind of like motion of objects. See figure 4 for a visual explanation. Actually, here we go. Why am I using my hands and my fists when I could just be doing this? The reconstruction loss is combined loss per Gaussian over all cameras. The reconstruction loss is going to, they probably don't mention it, but it's basically the ground truth image should be as similar as possible to the reconstructed image. And because the reconstructed image is the result of this differentiable rendering, which ultimately is based on this influence function, the reconstruction loss, or the difference between the ground truth image and the reconstructed image, is going through, the gradients are going through that rendering function, and then they're going into each of the Gaussians. So the reconstruction loss is probably, it's really only important at the very first frame, because that's the frame where they create all these Gaussians. But yeah, they're probably doing it over batches of cameras. So I don't know if they do all the cameras in one batch and then they do that many iterations, or whether they sample different cameras and then do batches of different cameras. We don't know exactly. Okay, we were looking at this local rigidity loss, though. For each Gaussian I, nearby Gaussians j should move in a way that follows a rigid body transform of the coordinate system between time steps. So we have Gaussian I here, this purple one represented by this I at time step t minus 1. So here we have 2 time steps t minus 1 and then time step t. So this purple Gaussian I, you see how it has some rotation. This ri t minus 1 and then ri t. So the relative rotation between those, right, that should match what happens with this Gaussian j. So here the vector that goes from Gaussian I to Gaussian j is this mu jt minus mu it, which is this here, mu jt minus mu it. So you can see here is the vector from I to j at time step t, and then here's the vector from I to j at time step t minus 1. So it's basically saying the vector between these rotated by this, in the inverse of this rotation matrix, which just puts it back into world coordinate frames, and then you rotate it again by the rotation matrix for the next time step. So that's basically giving you the difference in rotation, the delta r, if you will. And it's saying if you multiply that delta r by that vector, it should be the same as this. Yeah, I think the best way to think about that is like kind of the example I was showing with my hand. Maybe I'll use this, right, where it's like you want this point and this point, the vector, you want this point here to actually move like this. See what I'm saying? You have this rigidity. You want the relative rigid body transformation between them to kind of stay rigid like that. Which is kind of weird because you're doing that for every single Gaussian, right? So like obviously this Gaussian here is not going to want to move, you know what I'm saying? Like who's leading who? There's kind of like a weird situation happening here where every Gaussian wants to be the kind of the one that causes all the other Gaussians to move with respect to itself. But this local rigidity loss is for all Gaussians, right? You're summing this for all j in some neighborhood. So KNNIK, this means you're summing this rigidity loss for all I and j with some k nearest neighbors. That's what this KNN means. But then you're doing it for all Gaussians in the scene. So somehow that magically works out to the situation where you perfectly track this bat. Right, which is weird that it kind of just magically works out that way. Because you can also envision how this is sensitive to the number of Gaussians. So if you have one object that is being represented by 10 Gaussians and then another object that is being represented by 100 Gaussians. So let's say you had like the guy's hand here versus the ball. Maybe his hand is 100 Gaussians and the ball is only 10 Gaussians. Then there's going to be a weird effect where the rigid body transform loss here, local rigidity loss, it's going to be, the hand is going to almost want to pull the ball. I don't know, there's almost like a weird density artifact that could be potentially introduced here. Okay. Let's see, what time are we at? 9:42. All right, I gotta speed up here. Since we are performing online optimization, all of the all of the centers at time t-1, the rotations at time t-1, the centers for the next one are fixed, and we are optimizing mu it, rit, mu jt to ensure that they match the values in t-1. Up to the rigid body transformation defined by the change in Gaussian's i's own coordinate system. If I rotates, then j needs to translate in a way that is equivalent to rotating around the center of I. This loss also applies the other way, forcing the rotation to match the translation such that we obtain accurate rotation. Yeah, this is the weird part that I'm surprised it just kind of magically works. Even though we only optimize to match the rendered images, which isn't possible with a point-based representation. We restrict the set of Gaussians j to the k nearest neighbors of I with a k of 20. So not actually a huge neighborhood. It's actually quite local. So they weren't lying when they said a local rigidity loss. You know, it's not like for 300,000 individual Gaussian points, like you could have, I would have guessed almost like a k 100. But here k equals 20, which is actually kind of small. We weigh the loss by a weighting factor for the Gaussian pair. Weigh the loss by a weighting factor. Okay, so you have some weight. The weight is based on this hyperparameter lambda here, lambda w, which they kind of just arbitrarily set to 2,000, which gives a standard deviation of around 2.2 centimeters. Okay, so these Gaussians have a standard deviation. That standard deviation represents, in this case, space, right? Units of space. So it makes sense that you can interpret the magnitude of the standard deviation of one of these Gaussians in actual physical units like centimeters and meters. Calculate this with the distance between the Gaussian centers and fix it over the rest of the time steps. This results in the rigidity loss only being enforced locally while still allowing global non-rigid reconstruction. Yeah, so you're weighting it, and then you're also limiting it to these neighborhoods of 20 points, which means that it's only going to be enforced locally. The rigidity loss is both necessary and adequate on its own to achieve good results. Since the rigidity loss is applied on all points, it is applied in both directions between any pair I and j, and thus implicitly enforces I and j to have the same rotation. However, we found better convergence if we explicitly force neighboring Gaussians to have the same rotation over time. This is weird. So this is weird because you're telling this Gaussian here, right, that because this purple Gaussian rotated, you should actually be moving up here, right? It's like you're telling it that the relative position between this Gaussian and this Gaussian should stay the same. So you see here how it's not actually the same. Like ideally you would want that to be like this, right? But what they're saying here is they have a different one that forces them to have the same rotation, like this. So you're simultaneously trying to tell it to keep that rigid body constraint, but then also rotate in the same way, which is fucking weird when you have like competing losses like that. This one also has some weight. You're also normalizing it based on the k, as in the k nearest neighbors here. Or what is k? K is the total amount of nearest neighbors. Yeah, k equals 20. You're summing over all neighbors and then summing over all Gaussians. Here you have the quaternion, and you can do this. So you can invert a quaternion and then multiply it by another quaternion. And that's basically the same thing as this, except you see here, because they need to multiply this rotation by this point here, the mean of the Gaussian, you need to put it in a rotation matrix. But if you're just doing everything in rotation world, you don't need to convert to a rotation matrix. You can just keep it as a quaternion, take the inverse of it, and then multiply it like that and get another quaternion, and take the difference between those quaternions, and then the L2 of that. Q hat is the normalized quaternion representation of each Gaussian rotation. So normalization of a quaternion makes it a unit quaternion, which enables smooth optimization. We use the same set of k nearest neighbors and weighting function as before. So they introduced kind of a weird, sketchy hyperparameter here of this lambda w, and then this k equals 20, another sketchy hyperparameter, and then they use the same sketchy hyperparameters for the other regularization loss that is being applied here that in a weird way competes with this original regularization loss. So there's a lot of weird sketchiness going on here, but it kind of seems to work fine. Hello, Subhash. We apply L rigid and L rot only between the current time step and the directly preceding time step, thus only enforcing these losses over short time horizons. So this makes it easy, but it also makes it introduces kind of a way for error to seep in, right? You kind of get these, I forget what the exact word is, but it's like drift or something like that. But basically, as soon as you have a little bit of difference, then it's going to become bigger and bigger and bigger and bigger. And like, you know, ideally you'd have additional optimization steps between not just subsequent frames, but frames on larger time horizons. So like the optimization runs for subsequent frames, and then you run the optimization for one frame and then the frame 10 away from it, you know, something like that, which kind of like hierarchies of time, I think could be something that they would do here. Okay, sometimes elements of the scene to drift apart, thus we apply a third loss, the isometry loss over long term. Actually, boom, why am I conjecturing about things when they're just doing it right here? Okay, so now here's the third loss that they're going to use, and this loss is basically saying the mu j at time 0, so the center of the Gaussian at time step 0, and the center of the Gaussian I at time step 0. So the distance between these two Gaussians at time step 0 and the distance between, or the vector between these two Gaussians at time step t, there shouldn't be a huge difference between those. Right? That's what they're basically saying here. The L2, you're weighing it by this Wij. Your same thing here, you're summing it over all neighbors of a specific Gaussian, and then for all Gaussians in the scene, and then normalizing it based on the number of neighbors. But does this one compete with these ones? No, this one is fine. This loss, L ISO and L ROT, are fine. You could actually have both of these kind of working in tandem, and that's totally fine. You could imagine a scenario where this is actually bad, right? Let's say if I was holding like a ball that could split into two, and then I was going like this, and then I just like separated it, that would completely fuck with this loss here, right? Like if I just, let's say, let me try to grab something on my desk that represents this. But actually, even if I was doing this, with my hands, and I was just like sitting there recording myself, and then halfway through the video, I go like this and I separate my hands, this loss, this isometric loss here, is going to actually not like that at all, because it's going to want to keep the Gaussian that represents this knuckle and the Gaussian that represents this knuckle together, right? It wants those to be rigid over the long term. So it's going to want to pull those together. So there's a lot of different losses here that are kind of pulling in different directions. And generally when you have lots of losses like that are competing and pulling in slightly different directions, you end up having to kind of find magical values for hyperparameters, and those magical values for hyperparameters are specific to specific scenes and specifics to specific data sets, specific things. So generally not necessarily ideal. So weaker constraint in that instead of enforcing the positions between two Gaussians to be the same, it only enforces the distances between them to be the same. Each time step of a scene is optimized one at a time. Why did they write it like that? That's kind of weird. During the first time step, all parameters of the Gaussians are optimized. That first time step is super important, because this is how you're going to get the actual color and the shape and the appearance of the Gaussians. But then after the first time step, the size, color, and opacity are fixed, and only the position and rotation are applied. So basically it's like a two-part optimization process. The first part is creating this static 3D Gaussian splatting scene, and then the second part of the optimization, which is where you're going to have these three optimization losses, or these three losses here, is where you're actually going to be changing the position and the rotation. Our approach can be seen as first performing static reconstruction, followed by long-term dense 6DOF tracking. In the first time step, we initialize the scene using a coarse point cloud that can be obtained from running CalMap, good old CalMap, which isn't perfect, but instead we use available sparse samples from depth cameras. What? Note that the depth values are only used for initializing a sparse point cloud in the first time step and are not used at all during the optimization. So I think in the original paper that we read last week, there was, they compared whether you initialize from kind of a uniform grid or whether you initialize from a kind of sparse point cloud. So a sparse point cloud is just a point cloud that is sparse, aka doesn't have a lot of points. We use densification in the first time step in order to increase the density of Gaussians. So in this paper, this 17 paper, the one that we read, they also have this densification and pruning kind of steps where they either add more Gaussians or prune them depending on the opacity or how many there are in a local neighborhood and so on. We fix the 3D scene in the first frame for 10,000 iterations. Using 27 cameras, iterations render a single but complete image. For each time step, we use 2,000 iterations, 50 seconds, for a total of 2 hours for 150 time steps. So first part, which is creating the static scene, takes about 4 minutes. And then the second part, which is creating the dynamic kind of motion, is around 2 hours. We initialize the estimated Gaussian center positions and rotation quaternions by using forward estimate based on a velocity estimated from the current position minus the previous position. So this is kind of primitive, but they're basically taking the Gaussian and assuming that the velocity keeps going, right? But you can see how this wouldn't work if you had something hitting a wall or something like that, right? Because then you would initialize it from a point kind of inside the wall. Do the same for quaternion using normalized quaternions. We find this to be quite important to getting good results. We also reset the atom first and second order momentum at the start of each time step. So why is that important? That's actually kind of important because the atom optimizer has these momentum terms, and what those momentum terms are telling you is, okay, I've been taking gradient directions and I've been changing the value of this little weight. And the previous 4 times I changed the value of this little weight, I moved it in that direction. So I bet you that when you tell me what I need to do to change this little weight, right, when the gradient comes and says, okay, you should be moving in that direction, I'm actually going to move it a little bit more in this direction because that's where I seemingly keep moving this little weight parameter in, right? So in this case, you're not changing the weights of a neural net. In this case, you're changing the positions and rotations of a Gaussian. So if you didn't zero out the momentum terms of the atom optimizer, you would basically be accumulating this momentum, which would be saying, okay, well, this little Gaussian rotation matrix parameter has gone down for the previous 4 steps. Therefore, we should make it probably go down. But that's not what you want, right? Because the stuff can kind of move randomly, right? Like this bat kind of like first it's kind of moving in this plane, and then he kind of rotates it in this guy's head like it's static for a bunch of time, and then he moves it quickly. So the reality of kind of these particles in the real world, which are being represented by Gaussians, the fact that they're kind of like moving in a weird way like that means that since you're using the atom optimizer to optimize the position and rotation of these things, you probably want to zero it out every time step because you don't actually want this momentum term. I would have just done it without momentum then. I don't know why. If you're zeroing out the momentum terms of the atom optimizer, why not just not use the atom optimizer? I don't know. In our test, the subject's shirt colors are very similar to the background. We noticed that often the shirt was being mistracked as it was confused with the background, while more contrastive elements like pants and hair were being tracked correctly. Okay, so if you have a similar colored shirt to the background, it has a harder time. Makes sense. To increase the contrast, we also render a foreground background mask. Yeah, so here's where the little hack of like the background, foreground information is coming in against a pseudo-ground truth. We can easily obtain by differencing with an image from the dataset with no foreground objects are present. See, more shit that you have to kind of have beforehand. Also, directly apply a loss that background points shouldn't move or rotate and restrict above rigidity, rotation, and isometry losses to only operate over foreground points to improve efficiency. So this is like the part of the paper where it's like everything sounds so clean and perfect, and then they start telling you all the little hacks that they did in order to make it work. So basically what they're saying is that the losses here are only applied to points that have the background log it here as probably 0. 0 indicates foreground, maybe 1 indicates background, or maybe it's flip-flopped. But they're only applying this optimization to the foreground. And it also ensures that these losses are never enforced between foreground parts and the static floor. So you wouldn't want the static floor to maintain its local rigid body transformation with the shoe, right? Because the shoe can just like lift and move somewhere else. Since we are optimizing over 27 different training cameras, each of which has different camera properties, these factors contribute to variations in color representations. Thus, we naively model these differences by simply optimizing a scale and offset parameter for each color channel for each camera separately. So they don't want to have to constantly swap out these intrinsic camera matrices, right? What they're saying is that each camera has like a little bit of distortion on the actual color. So each camera, they're basically going to keep track of kind of a little offset for the true color. And you can almost see this as like an EMA. You know, it's kind of a similar situation. We optimize these only for the first time step and then fix these for the rest of the time steps. Tracking with 3D dynamic Gaussians. Where are we at? We're almost there. Page 9. Page 8, page 7, We're starting with page 6. After we have trained our dynamic 3D Gaussian scene representation, we can use it to obtain dense correspondence for any point in a 3D scene. So you can say this point corresponds to this point. To determine the correspondence of any point, we can linearize the motion space by simply taking that point's location in the coordinate system of the Gaussian that has the most influence over this point. So whichever Gaussian is the kind of densest or least see-through has the most influence for that particular pixel. We're just going to assume that that is the pixel, or that is the Gaussian that represents that point, which, using their analogy of this being like a particle representation of the world, it basically means that particle represents that thing. There is now a well-defined and invertible one-to-one mapping for all points in space across all time steps. We can use the same idea to track any 2D pixel location from any input or novel view into any other time step or view. We first have to determine the 3D points corresponding to an input pixel. We can render out depth maps for any view using the max rendering equation, but replacing the color component for each Gaussian with the depth of that Gaussian's center. Okay, so if you have a bunch of Gaussians, you know the 3D position of every single one of those Gaussians. Rather than saying, what is the color of this Gaussian? Let me add up all those colors and here's the color of the pixel. Why don't instead you say, okay, well, what's the Gaussian that has the maximum influence? How far away is that Gaussian center from the camera? Now I know a depth. Now I have basically depth image, which is how they're getting these depth images here. These are basically the most influential Gaussian center for every pixel. We prepare a dataset which we call panoptic sports. We take 6 subsequences. So panoptic, optic as in camera, eyeball, optical. Panoptic, many optic. Panoptic sports is sports with many cameras. So basically that's this right here. It's this guy swinging a bat in a giant geodesic camera dome. So you have juggle box, softball, tennis, football, basketball. Let me paint this red. This is our color for data sets. Visual results for 3 more: handstand, sway, and lift. We obtain 150 frames at 30 frames per second. So basically 4 seconds. Maybe a little bit more than 4 seconds. There are 31 cameras, which we split into 27 training and 4 testing. 0, 10, 15, and 30 are the test. Cameras are positioned roughly in a hemisphere around the area of interest. And that's important. That's another very strong assumption that, like, the cameras are kind of uniformly sampled around the object of interest. That's not the case, right? And that's one of the biggest differences between monocular video and these kind of like multi-camera setups, is that if all these cameras were right next to each other, these results would be way worse. And a huge part of these results is the fact that the cameras are kind of uniformly distributed around the entire hemisphere. So there's a lot of little things like that that make a huge difference. So you got to make sure to take those into account when you look at the results and how good the results are. Okay, the images that they're using are 640 by 360, kind of weird image size. Right? 640 by 480 is, I feel like, the more standard image size there. 10 available depth cameras synchronized to the current timestamp. Subsample these depth maps by a factor of 2 to obtain an initial color and projecting these points into the nearest training camera. So this is their initial, where they're initializing these Gaussians from, but you could have just done uniform initialization, which is one of the things that they do in the original paper. Points that do not project are discarded. This is the pruning and densification step. Obtain pseudo ground truth, foreground, background segmentation mask by simply doing frame differences between each frame and a reference frame from the dataset for each camera when no foreground objects are present. Also another kind of strong assumption, right? The lighting in these things is consistent at all points in time, so background, foreground shots are going to have the same exact lighting, but that's not the case for the real world. In the real world, you're not going to have this reference frame with the same exact lighting, especially if you're doing something outside where the lighting is going to change over time. We prepare ground truth trajectories, tracking the high-quality facial and hand key point annotations. For each person, we take 1 random face key point and 1 random hand key point. So they're tracking face and hand key points, which are some other explicit correspondence information, right? And then they're going to compare that to the correspondences that you get from this paper. They're going to call these ground truth trajectories, but they're really not, right? They're just the output of some other tracking algorithm, classical tracking, probably not, probably deep learning tracking that is giving you hand and face key points. We use camera visibility labels to determine if the first point in each 3D trajectory is visible and add these videos to projected points. Each 3D point is visible around 18 cameras for a total of 371 2D ground truth tracks. They're going to evaluate it on a couple different metrics here. I don't like any of these metrics, but you have structural similarity, you have LPIPs, and you have PSNR. I generally find these to be kind of like a little bit bogus. You know, you can game them. They're not very understandable. That's the reason I don't like them. I prefer just subjective quality evaluations from double-blind, kind of like placebo study, not placebo, double-blind user studies. I would say those are kind of what I want to see, but all right, kind of seems like it works. PSNR higher is better. Bold means higher. It's just kind of like barely higher. But that's kind of what I mean, is that it's kind of hard to look at this as a human being and say, like, okay, well, what is 27 versus 28 on PSNR? Like, I don't have a really good intuition about what the difference there is. SSIM is also slightly better comparing to 3GSO. 2D tracking. TNU Vox S, TNU Vox, Instant NGP, Particle Nerf, and Rs. Damn, this is a little higher, right? 2739, that's significantly higher. For 2D long term, we use the metrics from a recent Point Odyssey benchmark. So this is the 2D tracking here. So because you get tracking for free from this technique, they're basically saying, well, let's evaluate the quality of our tracking to not ground truth tracking, but the tracking that we get from these face and hand tracking things. Seems to be pretty much as good. Run this in a similar online mode. We also perform comparisons on the dataset of Particle Nerf, which includes 20 train and 10 test cameras. We compare Particle Nerf, Instant NGP, and TNU Vox. The new benchmark is defined as one in which each time step methods are allowed a certain number of ray renders and back propagation steps. So obviously a Nerf, the more ray samples you have, the better it's going to be. So they probably clip it to a certain amount of samples along a ray, or limit it so that it takes roughly 200 milliseconds per time step. For a fair criterion, reasonably fair comparison. Why are rotation matrices and quaternions multiplied by their inverse in the loss function? This is something that also done in the definition of a 3D Gaussian. Yeah, so let's answer your question. When you take the rotation of something, right? The rotation of something tells you the rotation matrix is telling you how much it's rotating to go from the world space, which is like the 0, 0, 0, like if someone just wrote 0, 0, 0 on the ground and said Z is up, right? That's called the world space. It's basically the fixed world. And then your rotation matrix tells you how do you rotate from this fixed world to get to the rotation of the object, right? So if you apply the inverse of the rotation, like they're doing here, you're undoing it. You're basically undoing that rotation. So you're going back into the world coordinate. So if you inverse the rotation at time step t and then rotate by the rotation matrix at time step t minus 1, what you're basically getting is the effective rotation between time step t and time step t minus 1. So it's like the difference. It's like delta r, right? It's like the difference in rotation between time step t and time step t minus 1. But just the way that rotation matrices and the fact that there's a world space and then a local frame a local space, you have to undo it. So you're undoing the rotation and then redoing the rotation, and that new is going to be the difference. Does that kind of make sense? It's like if I want to take the difference between two vectors, I just literally subtract them. But if I want to take the difference between rotations, which are transformations, I have to undo inverse one and then redo the other one. Hopefully that answers your question, Mauro. But that's why you have q negative 1 inverse q times q here, and then r negative 1 times r. So undo it, redo it. Does that kind of make sense? Kind of, maybe. Mauro, are you still there? Ablation results on the juggle scene of panoptic sports. Comparing particle nerve left and R's right. What are we looking at here? Oh, particle nerve dataset. Okay, so this is a synthetic dataset that they used, I guess, in the particle nerve paper, and you can see just how much cleaner the representation is here. But one of the things that they don't show here, which they did show in the original paper that we read, is that the amount of memory that it takes to store an explicit 3D Gaussian representation is way more than the amount of memory it takes to store a nerve, right? It's a lot less memory to store a little neural net weights, which are implicitly representing the scene, compared to what you're doing here with these 3D Gaussians, where you're explicitly storing the scene. Here's your ablation results. So what are the things that are mattering here? So here you have all your different losses, right? So they're removing each of these losses individually. This is the background. Your isometric, so keeping points the same. Your rotation and rigid. Rotation is making the rotations of nearby Gaussians the same, and then the rigid is making the rigid body transform consistent. And looking at these numbers, it doesn't actually look like they matter much for the view synthesis. You know, the view synthesis doesn't care about that, which makes sense because these aren't even applied for the view synthesis. For the tracking, lower is better. So we see how this rigid one makes it, no rigid is pretty bad. So the rigid constraint is actually leading to the best. Out of these ones here, it's the best in terms of making the tracking better. Yeah, like look at this. The L rot and L iso 1.91, 1.93 compared to full 1.90, so they really don't make that much of a difference. And here you have the 2D tracking. Same kind of scenario where really most of the juice is coming from this rigid body transform loss. Two methods we would like most to compare to are OmniMotion, adapted to multi-camera metric space, and map visibility estimations, since they seem like the most promising competitors. However, since no code is currently available for either, we are unable to run such comparisons. It's fighting words by people who haven't released their code either. You guys didn't release the code. Code coming soon. No. You can't talk shit about other people not releasing code if you don't release code either. We provide comparison results with pips to show a comparison against learnt method that was trained specifically for 2D point tracking and also one of the state-of-the-art approaches. Our method sees 27, while pips sees only 1 that needs to be tracked in. On the other hand, pips is trained on 13,000 training videos where ground truth tracks were provided, while our method has never seen any ground truth tracks. Okay, so they're comparing against this pips here, but it's not exactly the right comparison because pips is kind of like a deep learning based approach that learns from a bunch of training data, right? These 13,000 training videos versus this technique here is also a learn, but you're learning the parameters of these Gaussians, so you only need the data specific to the scene. Okay, so performs good, less than the width of a wrist. Median trajectory error of 2.21 centimeters. Method has a 100% survival rate, never losing the point to track accuracy value of 71.4. So I guess ground truth is red, but it's not really ground truth. It's like whatever you're getting out of your tracking, classic tracking algorithm. And then blue is the choosing one of these Gaussians and then plotting its position over time. And actually, it's interesting to note that the blue is actually smoother in some situations. Like look over here. You see this red? You see that the classic tracking algorithm is kind of like jaggedy right here, but the blue is a little bit smoother. Well, another thing they could do here is actually another regularization they could add is basically a velocity or an acceleration regularization that penalizes kind of jerky motion. That's something that you see in tracking papers that they could have added here as well whenever they're getting the velocity of the, or not getting the velocity, but optimizing the position and rotation of these Gaussians. You see here this Kinect camera? This is a Kinect camera right there, which we know from here that there's multiple Kinect cameras, 5 Kinect cameras. That's what this like long black bar here is. Okay, measure the 2D tracking ability compared to the 2D tracker. It's not a fair one-to-one comparison, but we achieve a 10 times lower median trajectory and we have much better survival rate. Okay, particle nerf. Data set relatively simple in terms of simple synthetic objects, but we're better than that. Okay. Augmented reality enabled by dynamic objects can easily be removed from scenes, duplicated, or added together. You can just, you can't do this with a nerf. In a nerf, you can't say, okay, give me this Tonka truck, but get rid of this base here, right? Versus with these 3D Gaussians, you can just select all the Gaussians that represent this base and just get rid of them, and then take this Tonka truck and add another Tonka truck. So the composability of 3D Gaussians is much better than what you would have in a nerf. Camera views can be attached, move as the scene moves. Objects can be scanned and added to dynamic scenes. The hat stays correctly as he does a handstand. Does this guy do a handstand? That's not a handstand, dude. That's... You're getting to like a 45-degree angle, dude. That's... Come on. Even he appears like it too. He's like, come on, I tried. He's like, yeah, I'm just trying. Okay. We show results on the juggle sequence of our panoptic, ablating various different components of our approach. We identify 6 key components, which are above. So this is the ablation study, which basically just shows that the rigidity loss is the best. In terms of key components, the rigidity loss, the background segmentation loss, and the color opacity size parameter fixing, and the forward propagation for time initialization are key to obtaining both good tracking results and improvement in view synthesis results. The rotation loss and isometric loss only provide very small improvement in the measured metrics. However, visually we found the reconstruction results to be much more coherent. This is exactly the type of shit that I'm talking about, is that LPIPs, PSNR, like SSIM, like those aren't, they're not the whole picture, right? Exactly as they said here, is that even though it seems like the rotation and isometric loss don't really move the metrics much, visually we found that they do matter a lot. That's key. That's an important sentence right there. Our dynamic 3D Gaussian approach also leads itself nicely to being used for editing of dynamic 3D scenes. Gaussians are independent subsets, can be easily added or removed from scenes. Very easy to compose. Creating realistic renders by composing multiple different components from different scenes can also very easily propagate edits over time. Logos can be added to surfaces in a single frame, and the colors of the Gaussians can be updated to reflect this change. So maybe kind of like a little sidestep here, right? Where compositionality is something that isn't really possible in, for example, a diffusion model, right? I can't take something from a diffusion model and where am I going with this? If the representation of your object is entirely implicit, compositionality is not something you get for free. But the magic of something like a diffusion model, especially a text-to-image diffusion model, is that language is compositional, right? I can say a rabbit on top of a turtle, and I can say a turtle on top of a rabbit, and by switching the order of the words rabbit and turtle, I'm kind of messing with the composition of the scene, right? So the fact that language has this property that you can compose it and take it things and move it around separately, I don't know, I just find that kind of interesting. How the compositionality of language allows you to have compositional control over image generation. All right, I'm starting to make less and less sense. Let's close out here to the finish. We are performing full 6DoF tracking. We can take advantage of this for all sorts of visual effects. We could put a camera as a first-person view. Same can be done for adding objects. Conclusions and limitations. While our method achieves excellent results, it is not without limitations. Our method is only able to track parts of the scene that are visible on the initial frame. I think one of you found this, John, right? John Egan? But we came to the same conclusion. I would completely fail to reconstruct new objects by entering the scene. Our method also requires a multi-camera setup and does not work for off-the-shelf monocular video. Again, if you only have a kind of small locus of camera and you don't have this perfect multi-camera setup with perfect extrinsic camera matrices and perfectly calibrated cameras, and you have them all uniform around this hemisphere, it's not going to work anywhere near as good. So that's a problem. Conclusion. In this work, we have introduced a novel method for dynamic 3D scene modeling, view synthesis, and 6DoF tracking that has relevant applications across entertainment, robotics, VR, and AR. Utilizing Gaussian elements to model dynamic scenes, our approach uniquely captures movements and rotations consistent with physical properties. The implications of our method extend beyond the immediate results, offering new avenues for real-time rendering and creative scene editing. Our approach, characterized by efficiency and accuracy, sets a promising direction for the future of research and practical applications in 3D modeling and tracking, underscoring the potential for future innovation in these fields. And this is work being funded by some kind of German government grant. I don't know what Verbund Project West AI is. But cool. All right, no appendices. Don't even need it. And that's the paper, guys. Let's scroll up top here. Let me take a big sip of this yerba mate, and then let's summarize this bad boy. Okay. So today, we read this paper called Dynamic 3D Gaussians, Tracking by Persistent Dynamic View Synthesis. This is work coming from some German universities and French university and my personal university, Carnegie Mellon University, USA. This paper extends the 3D Gaussian splatting paper that came out last week that we read on this channel, if you're interested, which basically represents a scene as a bunch of 3D Gaussians, right? 3D Gaussians have a variety of properties. They have a position in space. They have some rotation. They have some size, right? When you think 3D Gaussian, you should be thinking basically like a little bubble like this, right? And what they do in this paper is they just basically add dynamics to it. That's why the word dynamic is in there, right? So they add this fact that this Gaussian is going to be moving and rotating over time. So a dynamic scene is a scene that changes over time, and one way to think about that is say, okay, well, there's some little particles, right? This kind of particle-based mentality. The scene is composed of these little particles, and each of those particles, they can't disappear, they can't appear, so every single one of them must move somewhere. Okay, well, if they're here and they're moving somewhere, then that means that we must be able to say this thing moves and has a particular path that it traces over space-time. So with that kind of core assumption, they have two different optimization processes. The first one actually creates these Gaussians, right, with the little color and a certain opacity and a certain shape. And then the second optimization process is basically making sure that the motion of these Gaussians follows certain kind of like intuitive physical priors, right? One of those is rigid body transformation, which means that things that are close to each other tend to kind of generally move around with each other. And that's what this rigid body transformation prior is. They also have a prior that things that are close together should rotate similarly. That's what this rotation prior is. And then they also have an isometry loss here, which is basically saying things that are close together should stay together, and things and so on. So those three losses, which are combined and used for this second optimization process, ultimately result in a trajectory over time for every single Gaussian that you got from the first optimization process, which is giving you the color and the appearance of each individual little Gaussian. That first optimization process, which was largely explained in the first paper, they just kind of like go over it very quickly here, is basically based on a reconstruction loss where you're trying to say, okay, this image should look like this. I have a ground truth image from this point of view, and I'm going to back propagate through a differentiable rendering function, which is based around this kind of like tile-based rendering and splatting and kind of sorting, which all works very quickly on a GPU. But I'm going to take each one of those little Gaussians and basically move them. And it works quite well. It's actually relatively simple approach, but then they go ahead and they show how it works well, and you get a bunch of stuff for free. So you basically get free tracking. You can get these kind of like, you can put a camera at any novel view synthesis from any point, any one of these Gaussians. There is a bunch of little tricks that they have. So they have all these tricks with like background, foreground. So now you need a background data set to be able to say this thing is foreground, this thing is background. They have a couple different hyperparameters here. So the number of points that are considered local, right? It's 20. So the 20 local points. They have a distance there as well. So something around like 2 centimeters. But it works well. 850 frames per second. Super fast, real-time rendering. And what else can we talk about? I think one thing that they kind of gloss over a little bit is that there's very strong assumptions in this paper. So for this paper to work and all the results that they show, you need this giant dome that they're sitting in, right? This giant geodesic dome that has a bunch of cameras in it, 200 and 480 cameras that are all perfectly calibrated. You know exactly where these cameras are. They're all synchronized to a central clock system. And that means that it's going to be very difficult to do this with a cell phone, right? This is really only going to work in this kind of setup. So maybe great for video production or kind of like movie studios where you have these kind of domes, but not great for your house. And I think the other thing that's a little sketchy is that there are priors that they're assuming for the tracking to work. Those priors are based on certain assumptions about the real world that aren't always necessarily true, right? So like there's one thing that you don't see in any of these examples is, I think, situations or objects where you don't have a local rigidity, right? I brought the example of smoke or water or something that deforms, that would be more difficult to model with this. Any kind of situation where objects appear or disappear, maybe you're throwing something new into the scene, that's also going to be an issue. So there's a lot of like little caveats to this paper, but at its base level, they show really, really good results, and it's a very quick extension of the 3D Gaussian papers, so you got to give them props for the velocity of research here as well. But other than that, cool results. We'll see where people take it. And yeah, looking forward to that. Hope you guys found that useful. Thanks for hanging out. Thanks, Moro, Subash, Chris, John. They call me Ken. Radell, Emily, Lamb, John, Ed, Nifty Leuse, and Wave Function and Barlow Twin. Thanks for the question, guys. Hope you guys found that useful. And I don't know what we're going to be doing tomorrow, but for sure there's going to be a stream. So let me know what you guys want. Talk to you guys later. Peace.